We know that with a quadratic equation, the values for x that will make this equal to 0 are those x-intercepts. We can find those a variety of different ways, factoring using the quadratic formula, etc. If we now have an inequality, we're looking for a range of values for x. So in this case, we want what are all values of x that would make this quadratic less than or equal to 0, or in this case, what are all values of x that would make this quadratic less than 0. This particular one, we're looking for all values of x that are going to make that quadratic greater than 0, or in this case, greater than or equal to 0. We know it will equal 0 on those x-intercepts. Okay, so let's say we're looking for all values of x that when we substitute them into this left-hand side, we're going to end up with something that's negative, something that's less than 0. We want to begin, because it is a quadratic, by figuring out what are the roots of that quadratic. Where are those points where it will equal 0? And remember, a quadratic function can have either two x-intercepts, one x-intercept, or no x-intercepts. So the first thing I'm going to do is say, okay, let's say that this quadratic is equal to 0. I can factor this, if it's factorable, and get those key values. So in this case, we're going to have an x-intercept at 3 and an x-intercept at -2. So then we can actually go ahead and draw a number line here, and we know that we're going to have one intercept at -2. We're going to have another intercept at +3. So when x is -2, this quadratic will equal 0. When x is +3, this quadratic will equal 0. We need to figure out where this quadratic is going to be less than 0. So you can see that those two roots essentially divide our graph up into 3 regions. Let's try choosing a number in each of those regions to see what happens. I'm going to start in the center here. So 0 is a number within here that's easy to work with. So let's try taking 0 and substituting it back in. So if I take a look at these factors, it's going to be easier to use the factors than it is to use this. So I can really quickly see that 0 minus 3, that's going to give me -3. Now it's the sign that I'm concerned with, not the value. So we know that when we put a 0 into this first factor, we're going to get a negative number. When I put a 0 into that second factor, so 0 plus 2, that's going to give me 2. That's a positive number. When I multiply a negative times a positive, I get a negative number. So I know that any number within this section is going to be negative. And you can even go ahead and try different values if you want, but that 0 represents all numbers within this region. So everything in here will be negative. Now let's choose a number in this region. So let's go, I don't know, maybe -5. So I'm going to substitute -5 into the place of each of those x's. And when I do that, my first factor, I'm going to get a negative number. My second factor, I'm going to also get a negative number. A negative number times a negative number is a positive number. So I know that any value for x that is less than -2 is going to make that quadratic positive. And then let's try a number in this last region here. So I need an x value that's greater than 3. So again, we can choose anything. If we happen to choose 10, 10 minus 3 gives me a positive value in that first factor. 10 plus 2 also gives me a positive value. A positive times a positive is a positive. So I know that any number greater than 3 that I substitute back in here for x is going to give me a positive value. And this should make a lot of sense when we consider the parabola. So if I go back here, I can see that my y-intercept is going to be -6, and because a is positive, my parabola is opening up. So I'm passing through those two x-intercepts, and we can see that these 3 regions correspond to what the parabola is doing in regards to where that x-axis is. So we know that the values that lie on the x-axis make the parabola equal to 0. Any part of the function that is above the x-axis is going to have a positive region. Any part of that graph that lies below the x-axis is going to have a negative region. We know that these values for x, which make y 0, are those x-intercepts. The values for x, which will essentially make y less than 0, are going to be all parts of the graph that are giving us a negative y-coordinate, so everything below the x-axis, and all values for x that are going to, if this was make this greater than 0, are going to be all parts of that function where we have a positive y-coordinate. So let's say that we see a question and we're asked to determine the solution set for an inequality given and to graph that solution on a number line. So these are the two inequalities. I'm going to begin by considering the function. So I'm going to look for where are those values of x that will make this equal to 0. I can factor this to get those x-intercepts. So one is going to be at +3, one is going to be at -2, and I know that's where that parabola will lie on the x-axis. Those are my x-intercepts. We also know that we're going to have a y-intercept of -6, and the parabola is opening up. We can also complete the square to quickly find that vertex, and then we're going to sketch this parabola. These x-intercepts are the points that divide the graph into regions. So my first inequality, I'm looking what are the values of x that will make this less than 0. So where does that parabola lie below the x-axis? And we can see that will occur when x is greater than -2 but less than +3. So in terms of the solution, we're going to say x must be greater than -2, x must be less than +3. Any value within that region, when we substitute it back in, will give us a value less than 0. Because we're not equaling 0, we're not putting those equal signs on there. And again, you can always test a value, so choose any value for x in between here, substitute it back in, and you should get a negative value. Now, in terms of graphing this on the number line, because we are not including those values, we're going to use open circles for the -2, open circle for the +3, and it's going to be every value of x in between there. What are the values of x that would make this greater than or equal to 0? So we know it's going to be equal to 0 at those x-intercepts, and then if we take a look at the parabola, every value of x less than 2 is going to give us a value of y that will be greater. Every value of x that is greater than 3 is going to also be greater. So in this case, because we have that equal sign as part of the inequality, we're including those equal signs here, and we're using closed circles on the number line to show that we are including those values in our solution. So when you go to sketch the graph, you might want to even just draw this in pencil, and then depending on what inequality you have, I just tend to do anything that's below in red, anything that's above in blue. It doesn't really matter. It's just, I think, red negative, blue positive, and then we're looking specifically along the x-axis. So what are those x values where that parabola lies below or when that parabola lies above? This is the solution set here, and we can also illustrate those values for x on a number line that we can substitute in here to satisfy each of those inequalities. Let's try one more. So if I see a question and I'm asked to determine the solution set and to graph that solution on a number line, these are my two inequalities. But I know I first want to consider what that function will look like. I'm going to see if it's factorable, then I don't have to use the quadratic formula to try to get those x-intercepts. So I'm going to first of all factor out a -1, just so my leading coefficient is positive. I'm then going to factor it. I can see that I'm going to have an x-intercept at -1 and at +4. Those are the roots of the parabola, so we can also go ahead and sketch that graph here. I know that when x is -1 or when x is +4, this quadratic will equal 0. What values for x will give me a y value greater than 0? So essentially, where does that parabola lie above the x-axis? So I've gone ahead and sketched this. I know my y-intercept is 4. I know I'm opening down, and I just quickly completed the square to get the coordinate of that vertex there. And then we can see that we're not including the zeros on that inequality. My parabola lies above the x-axis for all values of x that are between -1 and +4. We're not including those, so we're going to have open circles on our number line, but x can be any value in between there, and we can write it like that. What are the values of x that will make this quadratic equal to 0? Well, we already know that, -1 and 4, so we're going to use closed circles. Those are included as part of the solution. Or we'll make this quadratic less than 0, essentially negative, so we're looking for those negative y values. So I can see that any value to the left of that -1 is going to give me a negative y value. My parabola is below that x-axis, and any value of x that is greater than 4 is going to also give me that negative y value. It's lying below the x-axis. And you can always double check. So choose an x value that is in this region, or in this region, substitute it back in, and make sure that you get the desired result. Inequalities allow us to solve problems where the solution is a range of numbers, not necessarily one or two specific values. These types of problems occur in medicine, in engineering, in business, and everyday life. We're going to conclude by looking at a revenue question, and we already established when we first began quadratics that we can determine the revenue by multiplying the price that we're selling an item for times the number that we happen to sell. So when we start a revenue problem, we always want to set up our brackets, put in what is the original price, what is the original number sold, and then how does that change? So in this particular question, for every 5-cent increase in fare, we are going to lose 1,000 riders. So our price for every 5-cent increase, we're adding 5-cent increases, we're going to lose 1,000 riders. So we need that N, remember, we go up 5 cents, we lose 1,000 people. We go up 10 cents, 2 increases, we lose 2,000 people. So 2 times that negative 1,000. We know we're going to have an inequality because we're looking for what is the range of fares that will bring in a revenue greater than $112,500. So when I multiply the price by the number sold, I want this amount that I bring in to be greater than that revenue. Set up the inequality, and then we're going to substitute in our revenue, and then we're going to algebraically work this out here. So I'm going to begin by foiling this out. I'm going to combine my like terms together. So I've got those two ends. And then because we're looking to maximize revenue, let's put this from standard form into vertex form so that I can quickly identify the vertex. So I'm going to complete the square by dividing negative 50 out of those first two terms. And then we're going to take half of this, square it to complete the square that gives us that perfect square trinomial. And once we have this in vertex form, I can find the value of n by quickly rearranging this. So I'm going to subtract this constant term from this piece. Then we're going to divide out that negative 50, get rid of that squared by square rooting, and then move over that 27.5 in order to isolate n. So start by subtracting that 137,812 and 5/10. Divide out that negative 50, square root. Remember, we're going to have a positive and a negative root, and then we're going to add that 27.5 to this side. This happens to be a perfect square. So if we square root 506.25, we're going to get 22.5. So one solution is n is 27.5 plus 22.5. Our second solution is 27.5 minus 22.5. Now, if we consider the graph, so let's actually sketch a graph here. In the place of my y, we have an r, and in the place of the x, we have an n. So this is my revenue. This is the number of increases. On the one side, I'm just going to graph this as a horizontal line. So this is our revenue that we're trying to generate. And then if I graph this vertex form here, I can see my vertex is going to be there. So again, this is just a rough sketch. It's not exactly perfect. And we can see that we're opening down. Now, the points of intersection are 5 and 50. If we substitute 5 back in this, I will get a revenue to equal 112,500, and the same with 50. We want to know when are we going to have a revenue greater than that. So we are above that line representing that 12,500 when n is between 5 and 50. So this is the number of increases that will generate that revenue greater than the amount we want, but we actually have to figure out what is the fare range that's going to get us that revenue. So fare is the price that we're selling those tickets for. So we're going to go back to the price bracket, and we know that we need greater than 5 increases or less than 50 increases. So let's substitute those amounts in here. So I'm going to take my price bracket, and let's begin by substituting 5 in for n just to get that lower bound value. So when I put in 5, I know that my price needs to be greater than $1.50. And then I'm going to do the same thing with my 50. I'm going to substitute that in, and I know that my price needs to be less than $3.75. So the range of fares needs to be between $1.50 and $3.75. We're not including those values because we don't want to equal $112,500. We want to be greater than that. And you can always choose a number in between here, substitute it back in and test to make sure that you are in fact generating that revenue that you want. And then I'm just quickly going to show you another way that you could have approached this. So at this step here, I then went into completing the square to turn it into vertex form. But if we wanted to leave it in standard form and solve it, I would move all of these terms over to the side where my squared term is positive. So we're going to move everything over to the left and have 0 on the right. So I'm just going to slide this up here so that you can see. So this is the quadratic that we would end up with. And then what I would do is see if this is factorable. So I can remove a greatest common factor of 50 from each of those terms, and then we can factor this. So now I know I'm going to have x-intercepts at 50 and 5. So 50 and 5 are when this is going to equal 0. I'm looking for when this happens to be less than 0. My parabola is opening up because my a value is now positive. So we can see that we're going to have a gain. N is going to be greater than 5, but it's going to be less than 50. So we end up with the same solution, going about it a different way.